Hello everyone, my name is Xinran and I'm from Xi'an Jiaotong University. Today, I want to talk about stochastic unit commitment model considering the impact of carbon emissions trading. And first, I want to talk about the background. Carbon emissions is the most fundamental factor leading to global warming. Countries around the world are actively building carbon emission trading market. Based on China's CET policy, a two-stage stochastic unit commitment model is established to analyze the impact of CET on power systems and renewable energy consumption. Next, I want to talk about the modeling. Based on the consideration of economic benefits, environmental effect, and renewable energy consumption, a two-stage stochastic programming model is established, which takes the minimum system operation costs, optimal carbon economy, minimum deep peak regulation costs, and minimum curtailment penalties of renewable energy in a year as the objective function. Therefore, the linkage of the power market and the carbon emissions market is realized. Besides, for each season, S kinds of renewable energy stochastic scenarios are considered, and the startup shutdown states of each unit remain the same in each scenario. Well, next, I want to talk about the constraints. The power balance of the power system is the balance between power supply and demand, and constraint 1 requires that the total power generation of the system and the total load should be equal at all times. Constraint 2 ensures that the power flowing through transmission lines cannot exceed their maximum transmission capacity under the DC power flow model. Constraint 3 ensures the system reserve capacity considering thermal units and renewable energy resources as the units providing spinning reserve. The unit states constraints, modeled as constraints 5 to 7, describe the on, off, and running states of thermal units using 3 integer variables. Constraint 5 indicates that each unit can only be on or off at the same time, and constraint 6 describes the logical relationships between the on signals, the off signals, and the working states of units. In addition, constraints 8 to 9 ensure that the continuous on and off states of thermal units should not be less than a certain time limits. Constraint 10 to 11 denote the safe operation boundaries of thermal and renewable energy units, respectively. The ramp-up, ramp-down constraints 12 to 13 mean that outputs of thermal units should be adjusted within safety limits. And note that constraint 10 is not a standard MIQP problem, and it can be further transformed into constraints 14 to 17 use the Big M method. Constraint 18 suggests that the carbon emission of each thermal unit should not exceed the sum of the initially allocated carbon emission quotas and the purchased carbon emission rights, while constraint 19 limits the number of purchased carbon emission rights. Moreover, constraint 20 means that each unit must purchase carbon emission rights to meet its targets. And third, I want to talk about the case study. The detailed information of Ningxia power grid in China is presented, and in addition to address the uncertainty of renewable energy output, 4 typical scenarios of renewable energy with different probabilities are selected for each season by processing the historical data in this region. First, the optimization results of the Ningxia grid throughout the year are analyzed. Figure 2 reveals that when renewable energy is relatively scarce, such as in winter, the renewable energy curtailment is small, while it is large in summer. Additionally, the deep peak regulation of thermal units in June and August is the most evident over the year due to the high slope of renewable energy change in these 2 months. Then the effects of the carbon emission coefficients and the carbon price on the optimization results are analyzed. August is chosen as a typical month to study. Comparing case A and case B, it can be concluded that when the carbon price remains unchanged, the reduction of the carbon emission coefficient will lead to the reduction of the total cost, deep peak regulation cost, and carbon emissions cost, while the operation cost of thermal units and renewable energy curtailment cost will increase. When the carbon emission coefficient is 78.5 kilogram per megawatt hour, if the carbon price increases to $0.035 per kilogram, the carbon emissions cost increases, the deep peak regulation of thermal units reduces, and finally, the total cost of the system increases. Further, when the carbon price increases to $0.07 per kilogram, the system tends to reduce the regeneration of thermal units as much as possible due to the sharp increase in carbon emissions cost. And finally, let's make a conclusion. This paper proposed a unit commitment model considering the impact of CET. In this model, stochastic programming is employed to deal with the uncertainty of renewable energy resources. Numerical results show that the decrease in carbon emission coefficients may lead to a higher renewable energy curtailment, at which point the renewable energy curtailment will first rise and then fall if the carbon price is further increased. Future work will explore the unit commitment model under the influence of more market and policy factors. And that's all. Thank you for listening.